After my last video, many of you asked for a deeper look at how I actually work with AI and the ESP32. So today I will show you a real example project. An iOS voice keyboard for any computer. After my last video, many of you asked for a deeper look at how I actually work with AI and the ESP32. But that's only half the story. You will also see how I automatically test ESP32 devices using an ESP32 workbench, a Raspberry Pi running special software that allows an AI agent to program, flash, monitor, and even test Wi-Fi and BLE behavior of ESP32 boards. The second part is a full walkthrough from the installation of Claude Code till the test of the project, if you want to see the extreme power of today's AI. Grüezi YouTubers, here is the guy with the Swiss accent, bringing you a new episode with fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you'll always sit in the first row. So what is this iOS keyboard project? I wanted to dictate text into any application on Windows or Linux, in English and in German, and ideally in other languages as well. Unfortunately, the Windows dictation system is quite limited, and professional software that does this properly can become very expensive. The speech-to-text capabilities of modern smartphones, on the other hand, are excellent. So I asked myself, why not use the smartphone for speech recognition and an ESP32 as a USB keyboard? The idea is simple. The smartphone converts speech into text, the text is sent over BLE to an ESP32, and the ESP32 pretends to be a USB keyboard and types the text into the computer. This means speech input for any application in multiple languages. Today we will build the ESP32 part of this system and test it. First a bit of theory, and then I will show you what actually happens in the terminal. To save you time, I will speed up the boring parts. Before starting the project, I had to solve two particular problems. Problem number one, serial ports. As I mentioned in my previous video, I run AI development inside containers in a virtual machine, because I want the AI to have full access to the development environment, but not to my main computer. Unfortunately, my Proxmox server only has one serial controller. And even though it exposes several connectors, they can only be used by one VM at a time. In my case, that VM is Home Assistant, which needs the Zigbee dongle. So there is no serial port left for the ESP32 programming. That is not really an AI problem, it is a VM infrastructure problem. Problem number two, realistic testing. Most ESP32 projects use Wi-Fi, sometimes BLE, and often MQTT. During development, I want to test situations like what happens if Wi-Fi disappears, what happens if the MQTT broker is offline, what happens if the wrong password is entered, does the captive portal work correctly, and so on. But I cannot simply turn off my home Wi-Fi or my production MQTT broker just to run tests. So I built something I called ESP32 workbench. It is a Raspberry Pi Zero 2W with a USB hub and several Python programs. This small system can connect multiple ESP32 boards via USB, expose their serial ports to the VM, create a Wi-Fi access point, enter data into a captive portal, switch Wi-Fi connections or MQTT broker on and off, and monitor serial output automatically. And the interesting part, the whole system is designed so that AI agents can control it directly. This means the AI can flash firmware, watch the serial log, run tests, validate the results, and fix problems in the code if needed. So the ESP32 workbench is really an automated hardware test lab. My overall development setup looks like this. The ESP32 is connected via a USB hub to a Pi 0. The Raspberry is connected to the VM via an Ethernet cable. Like that, Wi-Fi can be used for testing. If your computer has a serial port and you do not need automated testing, you can simply connect the ESP32 directly to your computer. The AI workflow. For development, I always work in the terminal using an AI coding agent. At the moment, I use Claude Code, but you could also try Codex or Gemini. Maybe by the time you watch this video, they will be equally capable. So as a first step, I installed Claude on my container and connected it to my account. It's not free, but I never regretted the money I paid for it. Because I want to grant the agent full access to the development environment, I let it create a shortcut called SuperClaude. That is not mandatory, but comfortable. From now on, you can wish what you want, and Claude will make it happen. For example, to install ESP-IDF or create a small Hello World program to test your plumbing. This has to be done only once per installation. I create separate Docker containers for each project, but this is not mandatory. My workflow always follows the same steps. Step number 1, create a repository. Every project starts with GitHub. I ask the AI to create a repository immediately. This protects me against any AI disasters, and it also allows me to share the project with you. During development, I regularly tell the AI to commit and push changes, so I no longer need to remember any Git syntax. Step number 2, describe the idea. Next, I create a project description. Recently, I switched to Markdown because it is rapidly becoming the standard documentation format in the AI world. This document only describes the idea of the project. Step 3, generate the functional specification. For implementation, we need much more information. For example, which MCU we use, how the ESP32 interacts with Wi-Fi, communication protocols, error handling, and test cases. Because many projects are similar, I created a standard operating procedure that automatically generates a functional specification document, or FSD. And because we live in the age of AI, I implemented this SOP as a Claude skill. Using this skill, the AI reads the idea document and generates a complete engineering specification, including test cases. Step number 4, implementation planning. With the FSD in place, I ask the AI to plan the implementation. Large projects are divided into phases to reduce complexity. Step number 5, code generation. Next, the AI writes the code and compiles it. Sometimes this step requires several iterations to fix compilation errors, but in most cases the AI resolves those issues without my help. Step number 6, flash the device. Once compilation succeeds, I tell the AI to flash the firmware to the ESP32. In my case, this is done through the ESP32 workbench. After flashing, the AI automatically monitors the serial output to confirm that the device starts correctly. Step number 7, run tests. Next, the AI executes the test cases defined in the FSD. If the tests pass, the phase is complete. Then we move on to the next development phase. This process repeats until the entire project is finished. Step 8, enhance your project. Usually, during the usage of the first version, I want to improve things. Either I write these wishes to the FSD and ask Claude to implement it using the steps from before, or I ask Claude directly to enhance the program and update the FSD. If you wish, you can now see how I implement all the steps I showed in reality. The entire process of building and testing this iOS keyboard, phases 1 and 2, took me about 1.5 hours. I did not cut the video, I just increased the speed of some parts. You will see in the video how many lines of code were needed for the project. First we have to install npm. Now we can check if it's installed. It is installed. Now we have to install Claude. And try it out. It works. Now we have to authenticate Claude with a subscription. We have to copy this string into a browser because we run on a headless Linux systems. And now I copied the code from the Anthropic page and we are here. Yes, I trust this folder. Use high effort. That's okay if you have an expensive Max account or so. Usually this is okay to work for a week with a high effort. If you only have the $20, maybe it's better to use the medium effort. Hello Claude. So it runs. So my first prompt is this one here. Make that when I type super Claude, it results in Claude dangerously skip permissions, internal and from SSH. And now Claude works. And this is the questions it always poses if you do not use dangerously skip permissions. Yes, do it. I want to avoid that. Done. So super Claude should work now. Let's check it. Does not work, so we have to log out and log in again. Super Claude, and now it works. Yes, I accept. And now we always have bypass permissions is on now. Now we can start with our project. Now the next thing is to install the ISP IDF only for the ESP32S3 chip for the moment, because otherwise we have a too big installation. And now this takes a moment and I will come back when it is installed. Now ESP IDF is fully installed and configured. Would you like me to set up a project or do anything else with the ESP32? Yes. Create a Hello World project for the ESP32S3. That is a good thing to test if our installation works. So the build is successful. We have the ESP32, the Hello World. Now we have to flash the binary file. The ESP32 is connected to the workbench, and I have to tell him upload the hello world bin to the ESP32 via workbench. Now let's see if this works. You see here the workbench. It has slot 1 and slot 2, and this is one ESP32 which has to be programmed via slot 1. This is the debugging port here. Now let's find out if it works. It uses the skills. It did not work, so it starts to debug. And flash was successful. The device has been hard reset and should now running check serial if everything is okay. So it rebooted the ESP32 and it says hello world twice. So everything is working as expected. Now we want our FSD. That's why I give it this new task. Use the iOS keyboard project idea .md file and create an FSD document for the project. Now let's see what it does with this. It found out that it should use the FSD writer skill, which is part of the workbench. It sees what kind of services it needs. Found out that it uses Wi-Fi and NVS to store things which were not written in the project idea. And now it writes a functional description. It said it's a medium complexity. So don't know what is a high complexity, but it has all these stuff we discussed before, the 3 phases, 49 functional requirements and so on. Everything should be here. Now let's have a look. Here we have the documentation with the goal, with the users, the system architecture, iOS, everything here, the architecture with all the different components, boot sequence, then the implementation phases, phase 1 the infrastructure foundation, phase 2 the USB HID keyboard, phase 3 the iOS app out of scope, then the functional requirements with must and should. We can correct now this everything, but for the moment I do not have the time. We want to have Wi-Fi provisioning. It seems that it wants to have a captive portal here. It has OTA updates, it has logging with UDP, which is over the network and not over serial. We have the configuration in non-volatile or storage or EEPROM. We have a HTTP server. I didn't ask for that, but this is always nice. Then we can see what happens. And then we have some non-functional requirements, which is usually a little bit high-level bullshit, but no problem. We have some constraint, risk assumptions and dependencies is usually for the ESP32 is not a huge thing. And then the interface specifications. It took already the definitions for the Nordic UART service, for the USB HDI keyboard, for the HTTP API. Then it has some internal interfaces, data models. Then it has the different keyboard layout. Then it has operational procedures, how to flash, how to OTA firmware update in the normal operation. It has even given it a factory reset and with recovery procedures. And then we have one of the more important things, we have test cases. And in phase 1, we have test cases, for example, BLE discovery and connection, and then some data transfer, the Wi-Fi provisioning test, of course. Here is the captive portal, exactly. OTA test, successful OTA update, logging test, serial boot, UDP boot, everything what I wished. The NVS test, that it persists configuration, then corruption recovery. It's incredible what kind of tests it does. It implements watchdog. I didn't ask for that, but it's always good practice. Then it has some BLE edge cases. Edge cases in computer lingo are special cases. And it's interesting sometimes what kind of edge cases the AI proposes. For example, disconnect during transfer, which is a reasonable edge case. Then rapid disconnect connect, and concurrent to a BLE and Wi-Fi, which is also not easy with the ESP32. Sometimes it creates problems. It knows that, and it wants to test it. And then in phase 2, it has also quite a few test cases. And then, of course, the acceptance test, the end-to-end dictation, speech correction, multi-language, then long-term operation, obviously, and it wants also to do an OTA. Now it's a good time to give it this task. Create a GitHub repo, create a documents folder, and push what we have. And we see here we have the YouTube repository, and we have the 2 documents from our project so far. And it's interesting, if you do not forbid it, Claude says, I also helped, so I want to be a contributor here. And that's okay for me, because you should know that I did this together with Claude. I do not want to hide that I work with AI, and you can decide if this is good for you or if this is not good for you. Now we continue and let the AI plan the project based on the FSD document written before. Now it enters into plan mode, and you see this here too, that it switched to plan mode. And you see here, it checks all the environment to understand in which environment the project has to be created. For example, I use dev containers. This is a very handy thing. It's not in the scope of this video, but if you are interested, maybe you Google what it is. For me, this works out very well. I have some skills that create such dev containers with everything needed for if I want to do a Python project, if I want to do a ESP IDF project, and so on. Then the dev container is created, and I have all the needed tools already in the container when I start. So you see, skills for me is a very important thing. I do not use a lot of standard skills from the internet. I made my own skills because my work here with ESP32 and the microcontrollers is quite special. Most of the skills I found is more for web development and stuff like that. You find these skills, the workbench skills, you find them in the repo for workbench. And now we have the plan. Let's have a look at it. The context, then the project structure with all the different files needed, the infrastructure foundation as requested in phase 1, in steps, Looks good. So it's not a small project here, you see. And then we come into phase 2. More steps, 15, 16. So everything is here. Now the verification of phase 1. Some testing and the verification of phase 2. So everything seems okay. Now we want to start the implementation. Yes, I want to start it, and I want still to bypass permissions, because otherwise it's boring. And now you see it's no more in planning mode, it's now again in execution mode. And you see it gets the information from the skills. And now it starts to write the code. A little bit faster than I would be able to do it. This is also typical for Claude. It creates a to-do list for itself with steps, and then it executes one step after the other. Now it started with step number 1. And again here you see the same thing: NVS, UDP logging, Wi-Fi provisioning, BLE NUS, HTTP server, OTA update, watchdog, and so on. So you see these are all standard ESP32, let's say, components which are used often in our projects, but now it uses this exactly for our purpose. And now I'm very interested how many lines of code this application will need and how many compilation errors are made by Claude. And sometimes it even writes things in parallel. And now the implementation is complete with all the infrastructure for phase 1 and for phase 2. And now I ask, can we test it? And it understands that it has to be built first and maybe also uploaded later. And now it builds the whole project using the ESP IDF. So something failed. And now it starts to search for what failed. It needs a forward declaration of a parameter. And it automatically corrects it. So one error, but now the build is successful. So it made one error. Now I'm interested in how many lines of code the project contains. About 3,000 lines of code. One error in 3,000 lines of code. Reasonable. For sure. Much better than myself. I would have had plenty of errors and searching for errors and so on. Now we want to upload. It finds the ESP32 at slot 1 as usual. And now it may need a reset. And because I connected the reset pin to the Pi 0, it can reset the ESP32 and also hold the GPIO 0 low for programming. But obviously, it doesn't choose. And now I asked it if it used the skills, because it looks to me that it has some problems which are not needed. And it says no, it did not. These skills are quite new and sometimes they do not trigger, and you have to pay attention. If you know there is a skill, sometimes you have to nudge it a little bit in this direction. And now let's hope that it works well with the skill. Looks good. You see, it programs. And now it's interesting what happens. Flashed successfully, all 4 partitions. No UDP locks yet. It's clear because it's not connected to any network, so UDP locking does not work. Now it looks for BLE. The firmware is running perfectly, and here we see the lock, so it can connect to the lock, to the serial lock, because we still do not have the keyboard running. In phase 1 we decided to not use the keyboard, because now, like that, we still have the serial to debug. That's always good. And you see it found some issues and it corrects it in the code, and now it has to rebuild it. This already happens during testing of the captive portal. So we see that is a second error. Next try. All phase 1 modules are running. Wi-Fi access point is this, and we check with our PC if we see it. Yes, I see it. Perfect. And also BLE is advertising and ready for provisioning. Now let's see what happens. Provision Wi-Fi and do the phase 1 testing. And now it starts again with some to-do list. The Raspberry Pi connects to the ESP32's captive portal, enters its Wi-Fi credentials, and then the Raspberry switches and offers an access point, and the ESP32, because it now knows the credentials, can log into the Raspberry Pi to do the further tests without bothering my home network. Everything is done in the test environment. And here we will see if it connects to the workbench and gets, it already got the IP address 0.7. Perfect. So program works fine. Now the UDP logs are flowing. Also this is okay. BLE works on the ESP32. And now we get test results all passing phase 1. Very good. Now phase 2 is finished and we have all tests passed here. Perfect.